Welcome to week 3 of our pre-recorded lecture. So this is the continuation of what we have seen last week. Last week we have, in order to recap a bit of what we have seen, we have looked into a magnetic circuit. So we have defined what is flux linkage, and its relation with what we call as a reluctance. So reluctance is the measure of difficulty of how of the magnetic flux to go through a certain section of a magnetic circuit. So we have seen that basically it was the section where you have air gap that it is the most difficult. All the MMF or magnetic forces that is produced inside your winding. So MMF is the product of the number of turns multiplied by the current, or what we call as current density. So the current that you circulate into your winding to produce or to push that magnetic flux through your magnetic circuit. And that amount of energy, magnetic energy, is consumed basically mostly for the flux to go through what we call air gap, right? So we have looked at into the relation that is analogous to the Ohm law. So the MMF equals to the flux multiplied by the total of reluctance. So we understand how to calculate the flux. And then we have seen at the end what we call as inductance. So inductance is basically a measure of how much flux linkage do we get per amount of current. So it is basically a measure of how strong is our magnetic circuit. So if the value of inductance was high, it means that per amount of current that we inject into our winding, it will produce a lot of flux linkage. So flux linkage and flux is more or less the same thing. Flux linkage is the total of flux, it's N multiplied by phi flux, right? So as we seen in last week. So now after knowing that, what we would like to do this week is basically using that principle of magnetic circuit, knowing that we can have a certain amount of magnetic energy circulated or stored inside our magnetic circuit. How can we use that? How do we do to convert that magnetic energy? So magnetic energy comes from electrical energy stored in the form of magnetic inside the magnetic circuit, and how do we use it in order to transform it, to convert it into mechanical energy. So the topic this week, the second topic for week 3, is electromechanical energy conversion principle. To start, let's define what a magnetic force is, right? So in order to convert that magnetic energy stored inside our magnetic circuit into a force, let's define what a magnetic force is. So magnetic force is basically the force that is produced by what we know as Lorentz force law. So before we go through describing what Lorentz force law is, let's predefine a bit about the energy conversion that we're going to talk about. So energy conversion from electric or magnetic to mechanical through the magnetic field medium can be various. So they are basically divided into the range of energy or power converted, right? So the thing that we're going to talk about in this particular subject is basically the third one, which we call electrical machines. So electrical machines is basically the continuous conversion of energy in an equipment that we can call as a large equipment like motors and generators, and they did not include the two first categories. So what are the first two categories? So the first two categories are also conversion of energy from from electrical to mechanical, or vice versa, but they are with a smaller range of power. So for example, there are transducers and actuators. So what we know as transducers, the example of transducers that we have, you might know, for example, sensors, microphones, and speakers. So this energy conversion, sensors, microphone, and speakers, they also convert electrical energy into mechanical energy. For example, in speakers, you convert small electrical signals into basically vibration and therefore compression of air that creates sounds. But that kind of energy, basically, in order to vibrate your membrane of your speaker, it consumes a very small amount of electrical energy. The energy conversion is very minimal, so it's low power, small signals, and linear input-output relation. So that's what we call as transducers. And then we have second thing which has a higher range of power that can produce forces, but they are not continuous. So there are force-producing devices like solenoids, relays, and electromagnets. So what is electromagnet? Electromagnet is basically an equipment that you power it to get the coil becomes for a moment a magnet that we use to basically for the purpose of, for example, metal scrapping to collect ferromagnetic material and basically take it out from the junkyard. Okay, so here we have figures of loudspeakers. So it's also energy conversion from mechanical to from electrical to mechanical via magnetic medium. Here we have basically a solenoid valve. So solenoid valve is basically a valve that opens and closes to allow, for example, circulation, a flow of liquid, for example. And the actuation, the turning on or turning off of it is basically using a principle of electromagnet as well. So that's what we call actuators. And the first one here, speaker, is called transducers. But now the thing that we're going to talk about, and therefore the equation that we're going to derive therefore is involving what we call electrical machines. So electrical machines mean we have quite a certain amount, large amount of windings inside that machine that carries quite a certain amount of current, therefore produce quite a continuous, quite a higher range of power continuously, right? So Fournier's law, back to Fournier's law. So what does Fournier's law say? Fournier's law says the force that is produced on a current carrying conductor. So imagine if you have a conductor like this that is carrying a current, and if it is placed inside a magnetic field, there will be a force acting on the current carrying conductor, and the force can be calculated. So the force is therefore a vectorial parameter. The force, but here FV means it is in density per volume, so it's a volumetric force equals to J. So what is J? J is current density multiplied by B. So B is the flux density or magnetic field. So the equation here is basically for when you write V is for a unit of volume, but it is also true for example, if you you multiply by volume, it is also true therefore for a certain point in a conductor. So imagine if you have a conductor where you have a point inside the conductor, and that point is placed, there is a current going through that conductor, and it is placed inside a magnetic field. The force on that point can be calculated as vectorial product of the current by magnetic field. So this symbol here is not multiplication, it is a product, a vectorial product. So it is basically J multiplied by B multiplied by the angle sinus between the vector current and the vector magnetic field. So you can help to find basically the force using what we call Lorentz right hand rules. You have your thumbs that's pointing or x-axis that's pointing the current direction, in which the current flowing inside the conductor. So here you have the conductor with the current direction, and then it is placed, for example, you're pointing at the with your pointing fingers the direction of the magnetic field. Therefore you get your third axis, the z-axis, or the other fingers, the direction of the force that is acting on the conductor. So the conductor basically will move towards the direction of F, or is experiencing a force of F. Okay, so just remember, this is not a multiplication, it is a vectorial product. So what does it mean by vectorial product? Vectorial product means if you have two vectors and you do the vectorial product of them, what you get is basically you'll get another vector. You don't get a scalar product, you get a vector product. You get another vector where the other vector has basically the direction that is perpendicular to B and J, to the magnetic field in the current, and the amplitude of it is basically equals to J multiplied by B multiplied by sinus of the angle between J and B, current and magnetic field. In order to illustrate or understand properly the production of force using the Lorentz force law, let's have a look at this example. So in this example, let's read together the question. A non-magnetic rotor containing a single turn coil is placed in a uniform magnetic field of magnitude B naught. Okay, so what happened here, we have these lines that is representing with a vector lines. There's a field line of a magnetic field, uniform magnetic field of B naught. So it is in direction, they call it as direction Y, right? And inside it, we place a rotor which contains a single turn of coil. So here we see two wires that represent basically the one single turn of coil. So this view that we are looking at basically is the cross-section view of the rotor. So you have on one side the rotor going into the paper, into the screen, and then on the other side is basically the conductor that have the current carry it with the current I coming out of the paper, right? So you have the coil going around the rotor like this, and what we see is on one side is the current going into the paper, and on the other side the currents going outside of the paper. So what else do we have? The coil sides are at the radius r. So the coil sides we have at the rotor over here, it is at distance r of the center of the radius, and the wire carries a current of an amplitude I. Find the theta, so the question asks find the theta directed torque. So find the torque. Theta directed means the torque that is following the direction of theta. So we know that if you want to calculate torque is basically the force multiplied by the radius, but the force need to be a tangential force to the radius. So here we have a radius, so we need to find basically the force that is following the direction theta over here. Okay, so that's what we call as theta directed torque. It means we need to find the force following direction theta, and then of course multiply by r to find the torque. Okay, we need to find the torque by the force following direction theta. But we need to write them as a function of rotor position alpha. So because we know that the coil here can, as the rotor rotates, the angle of alpha can change. So from, for example, from 0 to 360, and in function of the position of the rotor, position of the coil, the force or the torque might change. As we can see in the equation later, or previously, the equation is basically a vectorial product. So it is depending on a certain angle, right? So there are certain parameters that is given. So it's given I, the current equals to 10 amps, the magnetic field B naught inside which the rotor is placed equals to 0.02 Tesla, and the radius of the rotor equals to 0.05 meter. So it's 5 centimeter. So assume that the rotor is of length L 0.3 meter. So length of rotor means in depth, if you look in depth, the rotor or the length of the coil following the axis that goes into the paper equals to 0.3 meter. So how do we find this torque? So of course, as I mentioned just now, let's try to do this together. Let me take a pen. So what we need to do is basically, in order to find the torque, we need to find the force. So imagine if the force in this direction, and then we'll multiply it by r to get the torque. So we know that torque equals to force multiplied by the radius r. So the thing that we don't know here is basically the force F. So we need to calculate first. The strategy is to calculate and find the force F. So how many force F can we find on the rotor? We know that there is two conductors, so there will be two forces. Okay, so what does the Lorentz law says? Lorentz law says that the force on a current carrying conductor equals to B product vectorial with I. So it means equals to B I sinus theta with theta, the angle between B and I, right? So the force equals to B product vectorial with I, which is BI sinus theta. So if you look at, what we need to do is to find the vector B and vector I. So where is vector B? Vector B is the magnetic field in this direction, and vector I. So there is two force. We know vector I for this, but I'm gonna change colors. Let's say I'm take color yellow for this part. So I'm gonna call this as force 1. So force 1 for current that goes into the paper, and I'm gonna call force 2. I'm gonna take another color. I'm going to call force 2 for the force that goes outside of the paper. So we have two force. So you cannot use just you should calculate not just one force but two force, and both force will be equals to BI sinus theta. The things that change here is the direction of I. So we need to have a look at which direction does the force goes first. Okay, so let's have a look at the force on F1, force 1. So we see you use your right hand rules. So you have your current in your thumb's direction. You have your pointing fingers index, which is pointing the magnetic field, and then the rest of the direction will be pointing into the force. So if you look, try to do this with me at the same time. So if you're pointing towards the current, so you have the current through your thumbs, so the current goes into the paper, right? And then you have the magnetic field that goes upward. So you have your force basically going in the direction of the same direction as axis X. Okay, so can you do it with me? So current going into the paper, the magnetic field goes upwards. Therefore, you find the force F through the that goes in the same direction of axis X. So I'm going to draw the force F1. So force F1 is in this direction, force F1. Now let's have a look at force F2. What about force F2? So force F2, again, your thumbs, the current. So current goes out of the paper, so pointing towards you. And then the magnetic field goes upward, right? Therefore, the direction of the force that is experienced by the conductor wire 2 will be in the direction of minus X. So we're going to draw the direction of force F2. So force F2, I'm sorry. I'm going to erase this first. I cannot actually see my pen. So force F2, the direction of force F2, it is in the direction of minus X. So force F2 is in this direction. Okay, so if we just have a look first at the force F1 and F2, we have in force F1 it pushed to the right hand side, and the force F2 pushed to the left hand side. And when we see that F1 is on top and F2 is at the bottom, therefore what happened is that it will be creating a certain torque that will rotate the rotor somehow in the direction of minus alpha, right? If you add these two forces, what happens is the rotor is going to rotate in this direction in the opposite of direction alpha, right? So now we know that the rotor is going to rotate. There is a certain force on the two conductor, but the question is not just that. The question asks us basically to find the torque. Okay, so in order to find the torque, you need to calculate the forces first, and then you have to multiply by the R. So how do we calculate the force? So the force, let's have a look one by one. Let's take a look at force F1. So force F1, if we look at F1, imagine this is your conductor. You have force F1 in this direction. But what we need to do is we need to project the force onto the tangent of the circle, into the tangent of the rotor. So we need to project it on the axis that is being given, axis theta. Okay, so if you want to project on axis theta, we have the angle alpha over here. So it is basically, if we do prolong the direction theta and we draw a line over here with a perpendicular on this side, we also have the angle alpha over here. Therefore, the force on theta, F1, it is basically this force which is negative, and it is a negative a certain value. What is the value? The value, of course, we know that the value is bi equals to bi sinus theta. What is sinus theta equals to? Theta is the angle between the magnetic field and current. If you look at the magnetic field and current, the magnetic field, if I get my pointer, magnetic field is in this direction, current is in the direction of the paper. So theta, the angle between current and the magnetic field is 90 degrees. So sinus 90 degree is 1. So the product of F, basically in both cases, F equals to bi. Okay, so F here is just equals to bi. It's just that, for example, here, let's say the current here, we're going to call it is positive, so it's equal to bi. Let's say the current here, we're going to attribute to it a sign of negative, so here is equals to minus bi. But when it is projected to the axis theta, what's going to happen is it is not just bi, you need to project on axis theta, so it becomes bi sinus alpha, right? It becomes bi sinus alpha. Okay, but now we can see that it is negative, so it becomes minus bi sinus alpha. So you have to do the same thing for F2. If you look at F2, if I redraw again, so we have, this is the conductor, this is the circle, this is the direction theta tangent to the rotor, and we have our force 2 F2 in this direction. What we want to is basically to have F2 projected on theta. So if we draw a line that is perpendicular to theta, F2 on theta is this one, so I'm going to call it as F2 theta. Previous one, I'm sorry, here we should call it as F1 theta because it is on axis theta, equals to minus B1 sine theta. So here in force 2, back to force 2, there is also, of course, the angle alpha over here. I'm sorry. So we're going to find out that F2 theta is equals to F2 sinus theta, and not sinus theta, I'm sorry, sinus alpha. And we know that F2, just like previously, F2 also equals to BI, but now I is negative, so we'll be having minus F2 in the direction for a direction of F2. F2 now is in the positive of theta, so we don't have to put negative again. So now we have this force equals to minus F2 sinus theta. So we have, I rewrite again, F2 theta equals to minus F2, so F2 is BI, minus BI sinus alpha, I'm sorry, not sinus theta, sinus alpha. Okay, so we have the two forces now, F1 theta and F2 theta. Okay, there is something that's missing that we haven't included yet. That is basically the length of L 0.3. As I mentioned previously, the force that we're calculating, which is equal to BI sinus theta over here, is a force on one point. So we know that our rotor or our conductor has a certain length, so we have to multiply everything by the length L as well. So in the equation, we have to multiply by the length L, so BIL sinus alpha for both. So we can see that both, I'm sorry, I have to change color. So we can see that both forces are in the same direction. They are all minus, and the amplitude of them is basically equals to minus BIL sinus alpha, both of them. Okay, so this is basically expected. Why? Because in order for the rotor to rotate, the force acting on the rotor should be in the same direction, right? So if they are in the same direction, then you can on the tangential direction, if the force is acting on the same direction on tangential direction, then the rotor can rotate. So now what we're going to do next is calculate, of course, the torque. So the torque the torque T equals to F multiplied by R, and F, what is the force? We have two force, F1 theta and F2 theta. So it is basically the force should be the sum of those force, because when we look at our rotor, we have two conductor in it, so both force are acting on it. So it should be F it should be equals to F1 theta plus F2 theta. So if you we write the equation now, T should be equals to the radius R multiplied by 2 times, so that is minus, I'm going to put minus BIL sinus alpha. Okay, so that is equation, that is the equation or the relation that will give us the torque in function as a function of rotor position alpha. So let's have a look again. We'll recall the result just now. So we have the result just now. Let me see, I have noted. So the torque that we mentioned just now, torque should be equals to minus, so there was minus 2 BIL multiplied by the radius, so therefore multiplied by R sinus alpha, right? So this is the equation of the torque. So what you need to do now is just replace with the values. So we know that B, it was given equal to 0.02 Tesla, I equals to 10 amps, if I'm not mistaken. L equals to 0.3 meters, with R equals to 0.05 meter, 5 centimeter. And alpha, it is a variable, so it's going to be depending on alpha. So you will find the equation for torque T equals, if you do the calculation, it should be minus 0.006 sinus alpha. So what can we conclude from this equation? What we can conclude from this equation is that the torque is depending on alpha, on the angle. So depending on the position of the rotor, the position of the of your conductor inside the rotor, with regard to the direction of magnetic flux, the torque produced is will change. So let's have a look. Let's try to plot the torque versus the angle of alpha. So we know that is equals to minus 0.06 sine alpha. So if alpha equals to 0, we're going to plot it in one rotation, right? So in one rotation, you're going to have, at the maximum, you have one complete rotation will be equals to 2 pi radian, so alpha in radian. And half of the rotation, you're going to have pi radian. So pi radian is basically 180 degrees. 2 pi radian is 360 degrees of rotation. So let's have a look at 0 degree or 0 pi. What will happen? So if you replace here with 0, alpha equals to 0. So sine 0 is 0. So you will get 0 torque. So if your conductors is over here, what happen is your rotor, your rotor of your machine will not produce any torque at all. Okay, you will not produce any torque. But what happen if theta equals to 180 degree, or let's have a look if alpha, not theta, I'm sorry, is if alpha equals to pi over 2 or 190 degrees. So if the position is now over here, let me see. So if it is positioned over here where we have pi over 2, you will have basically sinus pi over 2, and sinus pi over 2 is equals to 1, right? So here at this position, you'll get the maximum, which is minus 0.006, because sine alpha equals to 1. So it will be somewhere over here. And then if you go to pi back, so pi is basically in this direction, half of the rotation, you'll go back to alpha equals to 180 degree, therefore sinus alpha will become 0, so you'll be over here in terms of torque. And if you go into 2 pi, into 3 over 4 pi, 3/4 pi, what happened, you will have your torque, therefore here at the maximum, because you have minus sign, and here it will be equals to minus 1, so minus become positive, 0.006 over here. And if you go back to 2 pi, which is this position, then you'll have back at 0. So if we plot the graph, so it is a sine wave graph where you have minimum and maximum. So you have one period of torque as the rotation of the rotor goes in one rotation. Okay, so what's going to happen is that you will have a minimum point of torque when you are over here, and you have maximum of torque when you have over here. You are over here, but you have 0 torque when you are at 0 degree, or you are at pi of half rotation. This is basically expected and predictable. Why? Because we know that the forces is either in this direction or in this direction. If you are situated in 0 degree or 180 degree, when you have all the forces at the end on x-axis and pulling outwards, what happens is just create a force that basically contract the rotor, but it doesn't produce any torque. In order to produce torque, basically the force need to be so the maximum is basically when it is over here, right? And in between, you'll be creating a force that is in the middle between 0 and either maximum or minimum. So what we can see is that in function of position, you might have a negative torque, positive torque at maximum value, or there are certain positions where you might have zero torque, right? So in the principle of machine, what we want to do, if you want to use in practical your machine, we want to always produce a certain value of torque. So in practical, what we do is basically, what we need to do is that when we reach a certain place, for example, when we reach the position where we know that the torque is going to turn to 0, what we do is we have to switch the direction of current, right? We have to switch the direction of current so that the force becomes in the opposite direction. So for example, if we know that in this if our I'm sorry, let me take another pen. Let's say if our conductor here is now over here, and we know that if the current is in this direction, we would have the force in this direction. So you're gonna rotate like this. I'm sorry, it's not. You're gonna rotate in this direction. But if now the position is a switch, so this is if this conductor now becomes to the bottom, which becomes like this. Therefore, the torque will be in the opposite direction, right? So it will be in opposite direction. In order to make sure that the torque continues in the same direction and not goes into opposite direction, what we need to do is, once this conductor in blue here arrive in yellow position, we need to switch. Instead of having the current goes into the paper, we need for the current to goes outside of the paper like this. So in order to switch the direction of current, that's what we're going to look at later in DC machine, DC motor. We use what we call as a commutator or contactor, commutator and brush, basically to change the direction of current that we send onto the rotor. So that's more or less on the elementary principle of a DC machine. So we know now that in order to rotate a machine, we can produce a force by carrying a current inside a conductor on a rotor. So this is one method. So to calculate the force, we use Lorentz force law, which is the vector product of magnetic field and current that produce the force. And then, of course, in order to calculate the torque, you need to project the force on the tangential direction of the rotor. So that's what we have been doing. So please try to do it on your own, this exercise, to make sure you understand the mechanism of the production of force and how to calculate the torque and identify the position in which we will obtain maximum or minimum torque. And we can see that the torque basically switch direction in function. So it switch direction, right, in function of alpha. So that's about it on calculation of forces, therefore torque, inside a machine using what we call as Lorentz force law. Next week, what we're going to do is we are going to look at the calculation of force and torques in electrical machine as well, but not using a Lorentz force law. We're going to use what we call as the energy method. So instead, going through the equation of Lorentz force law, because basically not all machines are as simple as DC machines. Other machines are more complex, where we have more conductors and they are not always continuous current like here. So for example, here we have the current which is continuous, I equals to 10 amps. We might have variation of currents which is not necessarily DC and not as simple as this one. So what we're going to do is we're going to use a method that is that doesn't look into the production of force using the Lorentz law, but we're going to use a method that takes the form of abstraction, that use the principle of energy balance. So by calculating energy, so we know that, for example, we supply an electrical energy and then it is stored in magnetic energy and it has to be transformed into mechanical energy. We'll have a look at that next week. So this week is just talking about production of force using Lorentz law. So I'll see you next week in the next pre-recorded video lecture. Thank you very much.